The last thing that I'd like to do in this set of lectures on thermal radiation is to give you a brief glimpse to the process of how we solve thermal radiation problems. And what I mean by that is just what is the process via which we link the thermal properties of a surface to the electromagnetic energy that is being emitted, absorbed, and or reflected by it. And we'll find that this is considerably more complex than solving problems that involve conduction or convection. Not just because of the fact that the equations are more complex, they certainly are, but because of the fact that the geometry leaks into the description of the problem in an unexpected way. To illustrate this, consider the following physical setup. Let's suppose I have some sphere with outer surface, which we've labeled 1, that is enclosed by a spherical shell whose surface I've labeled 2. And there's no matter in between surface 1 and surface 2, and so the heat transfer that occurs between these two surfaces is purely radiative. Let's also assume that each of these surfaces is kind of the primitive object that we're dealing with. We're not necessarily going to consider specific points on each of the surfaces. We're going to assume that the symmetry of the problem and the geometry is such that we don't actually have to consider the subtleties of temperature variations at each surface, but that the temperature over each individual surface is uniform and that the nature of the radiation that's being absorbed, emitted, or reflected is also the same everywhere on the surface. Okay? Regardless of this simplification, we're going to find that the geometry is still going to be a source of headaches. And the reason for this is that if you consider, for example, the light or electromagnetic energy, however you want to think about it, that's being emitted or reflected off of a given point on surface 2, depending on the angle in which it is traveling, it is either going to go from surface 2 down to surface 1, or it's going to go from one point on surface 2 right back to surface 2. And so this is an issue because we can't just assume, oh, all of the radiation that's being emitted or reflected by an object is going to go into the other object. All of the stuff that leaves one surface enters the other surface. We find, right, that we have this geometric feature where now we have to consider that the geometry influences how much of the stuff that leaves a surface enters another surface. How does the geometry influence? Well, we see that this is something that can happen for this spherical surface 2, but we can also see that this is not something that can happen for this spherical surface 1. If you think about it, right, any little ray of light that is emitted off of the surface, no matter in which direction it's going, as long as it's actually leaving at some point that surface, it will always go and hit surface 2. And you can imagine that the amount of light that leaves surface 2 and hits surface 1 is a function of how large that central sphere 1 is. Okay, so the geometry 100% plays a role. All right? And so in order to tackle this issue, we first have to come up with some kind of metric that tells us the average or net heat flux that's leaving a particular surface. All right? So the only thing that we're trying to define here, which I realize might be a bit confusing, is that we are trying to basically create the net outgoing radiative flux per surface area of a given surface. Okay? So we would calculate the total outgoing radiation off of surface 1 or surface 2. We would divide it by the surface area of that surface. And then we would create this kind of average heat flux, or electromagnetic energy flux, pardon me. We would create this kind of average electromagnetic energy flux that is referred to as a radiosity, right? And from the perspective of the analyses that we've done before, the radiosity is the sum of two different things, right? It's the sum of the emitted electromagnetic energy flux off the surface and the sum of the reflected electromagnetic energy flux off that surface. Now, the emitted portion, we know how to model relatively well. We already calculated that energy flux is just the emissivity times the Stefan-Boltzmann constant times the temperature of that surface to the 4th power. And so we can calculate and relate this emitted portion to the thermal properties of the surface relatively easily. However, the reflected portion is a bit of a nightmare. And the reason that it's a bit of a nightmare is because how much gets reflected depends on how much is incident on that surface. And how much is incident on the surface depends on the geometry, right, of the setup. So how can we characterize, this feature in the geometry that tells us that some of the light that leaves a surface will not go into another surface, or that it might reflect back into itself? How do we characterize the amount of outgoing radiation that goes from one surface to the other? Well, we can create what's called a view factor. And all the view factor is it tells you the ratio, proportion, however you want to call it, the fraction of the amount of radiation that leaves one surface, the radiosity, I should say, the fraction of the radiosity that leaves one surface and then enters the other. And so therefore the view factor has two indices, which I've labeled as I and J, and those indices represent surfaces, right? So based on this arrow that I've used here, hopefully illustrates the way that we create or name view factors. If I wanted to understand the fraction of radiation that leaves surface 2, the radiosity, the fraction of the radiosity of surface 2 that hits surface 1, we would consider the view factor F21. If we wanted to consider or think about the fraction of the radiosity that goes from surface 2 back into surface 2, then we would just analyze the view factor F22. Based on the conclusion that we determined before, for example, we would find that since no outgoing radiation hits from surface 1, hits surface 1 again without at least bouncing off of surface 2, we would have that this view factor F11 is just 0, okay? And so the view factor is a comfortable way to define, right, this geometric feature. It's a way to basically put numbers to the fact that not all outgoing radiation from one surface impacts another surface, okay? And so there's a couple of nice features that are associated with view factors when it comes to doing calculations. For example, the principle of reciprocity. Now the principle of reciprocity says that, well, notice, right, that at every point that I have an outgoing light ray, if one light ray is able to get from, say here, surface 1 to surface 2, then there should be another light ray that's traveling in the same path, just backwards, that can go from surface 2 to surface 1, right? And the fact that we make this assumption, which is just a geometric statement, there's no real physics behind it, means that we can come up with the following relationship that relates the view factors of two different surfaces to each other and then also to their respective surface areas, okay? So this is pretty convenient if we don't necessarily know the view factor for one surface, but we do for the other, which may be the case whenever I have an object that consists of, say, a simple geometry or a simple surface, and then something else that is a complex or, tricky surface. Another thing that we can consider, right, is that remember that the view factor is a fraction. It's a fraction of an outgoing flux. And so what that means is that if we are working with an enclosure, so for example, radiation that is not emptying out into empty space, like the scenario that we have here where, the empty space where the radiation is occurring is all, within or between surfaces 1 or 2. Whenever we have this kind of enclosure situation, we can observe, of course, that even though not all of the radiation from, say, surface 2 has to go into surface 1, that it does have to go into a surface. And so that means that the sum of all of the view factors from each of these surfaces over the index associated with the kind of incoming surface, so the surface in which the radiation is going to impact, if we sum over that index all of the view factors, we would get 1. And that just has to do with the fact that the radiation has to go to a surface. It doesn't have to all go to surface 2, but it does have to go to either surface 1 or surface 2. And that's what this sum, this enclosure summation, is telling us. And that can give us some information about, for example, well, if we can figure out how much of the radiation from surface 2 is going to surface 1, then we can figure out from this enclosure property how much of the radiation from surface 2 is going right back into surface 2. So this is just one of the things that we can use to try to find expressions for view factors without having to actually do explicit calculations, based off of geometric or first principles to determine them. Okay? So why is this useful? Well, for every surface, right? So think about how the number of view factors scales with the number of surfaces in your problem. We have 2 surfaces in this problem. How many independent view factors do we have? Or not necessarily independent, but how many potentially independent view factors do we have? Well, we have the view factor f11, which we had determined was 0. We have the view factor f12, which, based on the fact that f11 was 0, from enclosure summation, we can find that f12 is equal to 1. We have the number, or the view factor f21, and we have the view factor f22. That just means that we have 4, right? And we can extrapolate this to any number of surfaces to realize that the number of view factors, maximum number of view factors that we can have in a problem, scales with the number of surfaces squared. So why is this an issue? Well, remember, we're dealing with these surfaces as kind of primitive objects, which is a problem if we're trying to understand the way that the temperature varies over said surface. So what is one way that we can try to deal with that issue? Break the surface up into more pieces. So what if, for example, I decided to break up surface 1 into halves? So, I split it down the half here, and I split it down the half here. And now I have 1, 2, 3, 4 surfaces. And then now I have 4 squared view factors. So now I have 16 view factors. You can see how this can quickly run away into a very problematic issue. Because now, for example, if we actually wanted to do a realistic partition, where let's say that we wanted to split up, create, let's say, let's suppose that we did a partition where we generated something on the order of about 100 surfaces, right? Well, 100 squared now becomes 10,000. And so as you start building up the number of surfaces in your problem, as you start increasing the resolution of these sorts of systems to something where you can actually try to study the temperature as a function of location on the given object, or on the given surface of the object, I suppose, you start to get so many different equations involving so many different factors that it becomes completely impossible to do for a human, and it starts to become difficult for a computer to do it. You need dedicated software that has the ability to process a bunch of equations simultaneously in order to be able to handle so many view factors, so many different parameters. Okay? And the other thing that is tricky, of course, is that the radiosity, which is associated with each surface, then plays in to a calculation associated with the incoming radiosity from the other surfaces. So take a look at this equation, right? This tells us the radiosity off of a given surface I. But the radiosity off of that given surface is a function of how much is being reflected, which is a function of the incident radiation, which is a function of the radiosity of the other surfaces, and the view factors that modulate how much of that radiosity from the other surfaces actually impacts, the surface that we're currently considering. And so it turns out, right, that all of these radiosities show up in basically coupled equations, all right? And so this becomes a very big nightmare. So what is one strategy that people like to employ? What is the actual process when we have to solve a thermal radiation problem? What is the mechanism that people utilize in order to try to solve these sorts of problems? Well, what we create, perhaps unsurprisingly, is something that's called a radiation network, which is a very similar thing to the thermal networks and the thermal circuits that we had constructed before. So how do we construct these radiation networks? Well, the natural first step is for us to try to ask ourselves, what are the analogous quantities to the primal things that we were considering when we were analyzing thermal networks for conductive and convective systems, right? Over there, the things that we really cared about were heat transfer rates and its relationship to temperature differences. And then we created thermal resistance based off of that linear relationship. We have to try to see if we can construct a linear relationship between two similarly primal quantities for radiative problems. And the natural successor for, at the very least, the net heat transfer rate between two objects is to consider the net electromagnetic energy transfer rate between two objects. Okay? And so we define it with the risk of confusing us into thinking that this is a heat transfer rate. We think about this net electromagnetic energy transfer rate, Qij, that's happening between, say, some object or surface I and some other object or surface J. And so we can think of this as being how much, electromagnetic energy, what's the rate at which electromagnetic energy is being transferred from surface I to surface J. And that's going to consist of two contributions. The first contribution is going to come from the amount of radiation that leaves surface I and hits surface J. That's going to be the radiosity of surface I times its surface area times the view factor between surface I and surface J. And so this is the net outgoing radiation off of surface I, and then this view factor tells us the amount of that radiation that's going into surface J. This is, of course, offset by the amount that's incoming from surface J into surface I, which is represented by this multiplication, of course, the radiosity of surface J times its surface area multiplied by the view factor that is associated with the amount of radiation that goes from surface J to surface I. We can use reciprocity to simplify this equation, right? Because we see that we have a product of a view factor and a surface area. And so we can utilize reciprocity to reframe this same equation in the following form, where now we have the same surface area and the same view factor multiplying a difference in radiosities. And this illustrates, this kind of provides for us the natural analogy, right? All we have to do is to observe, oh, the net electromagnetic energy transfer rate multiplied by 1 over this product of a surface area and a view factor is equal to the difference in radiosities between the two surfaces. And so now the radiosity is taking the role of a temperature difference, and this 1 over AF factor takes the role of a resistance, right? Which is usually in the context of radiation networks called a space resistance, okay? So now that we've created this, well, how does this help us construct a visual interpretation of the radiation that's, for example, being exchanged between this surface in this example? Well, what is the net energy that is being transferred from a single surface, okay, to everywhere else, right? Well, Qi is just the sum of all of these Qij's over J, right? So the amount of energy that goes, or the rate of energy transfer from a given surface has to be equal to the amount of energy that's being transferred to each individual surface added up over all of those different surfaces. And this is very similar to the equation that we had constructed for analyzing currents in parallel circuits. So we had said, of course, that resistances add up inversely in parallel thermal networks before, but we noticed, right, that through each individual little junction that we find that the currents have to add, right, that they split and then add back up. And how we can represent that from the perspective of a thermal network, at least a thermal network that represents this system, well, if radiosity is serving the role of temperatures, then it makes sense for us to construct a little node. A node that represents, let's say, surface 1 with radiosity J1, okay? We can then connect this node to another node, which represents surface 2, okay, which has some radiosity J2. And the beautiful thing about this, of course, is that we can then connect, or try to interpret, Qij as being the amount of energy, or the rate at which energy is being transferred from 1 to 2. And so whether or not that number is positive or negative, whether or not Q12 is positive or negative, or whether or not Q21 is positive or negative, depends on whether or not J1 or J2 is larger. Okay? And then this thermal resistance that we've drawn between them is simply the thermal resistance that we had created before, right? And the nice and beautiful thing about this, of course, is that because of reciprocity, it actually doesn't matter what the indexing is. So we had earlier written that it was something like 1 over AI Fij. So you might ask yourself, do I put the 1 or the 2? Is it A1 F12 or is it A2 F21? It actually doesn't matter. Either of them is fine as long as you maintain, right, the right notation. And so this resistance, this space resistance that happens between these two elements, pardon me, is simply going to be a nice and normal function of AI Fij, or A1 F12, A1 F12, or equally, right, this will result in the same quantity from reciprocity, A2 F21. Now, what's the problem here? The problem here is that we now have to ask ourselves, oh, wait, hold on a second. Energy is being transferred from surface 1 to surface 2. But hypothetically speaking, right, we also have this energy that's being transferred from surface 2 to surface 2. We have to account for that too, right? Well, not really. And the reason that we don't have to account for it is, of course, because we are considering the net heat transfer rate from one surface to the other, okay? And so the net energy transfer from one surface to the other, when we are considering the same surface, is naturally zero. And so self-interactions are actually simplified a little bit when it comes to understanding, you know, the way that we represent properties through radiation networks, like that complicated little annoyance of having non-zero view factors involving the same surface isn't something that we have to worry about too much when we are analyzing systems using thermal networks. We only care about different surfaces. And so in this particular scenario, it winds up being the case that this is a super simple thing to consider, right? But the only reason that this is a super simple thing to consider is because of the fact that we have two surfaces, okay? If we had three surfaces, this becomes an even bigger nightmare, all right? It starts becoming more and more complex. Why is that? Because now we have to consider, for example, let's say we have J1 and we have J2 and we have J3. Now we have to consider the radiation that's leaving surface 1 and going to surface 3. But we also have to consider the radiation that's leaving surface 1 and going to surface 2. And then we also have to consider the radiation that's leaving surface 2 to surface 3. And so we get, you know, this interesting little architecture for a thermal network that is a little bit more complex. Now, of course, I'm not saying that these problems in particular are huge nightmares. These are just, you know, three surface systems. But remember that because we're treating the surfaces as primal objects, we have very, very poor resolution whenever we're working with thermal networks that are this small. When, in order to actually work with real systems, in order to get estimates of how temperatures change over surfaces using radiation, we would have to construct so many nodes and construct connections between all of those different nodes that very rapidly this kind of analysis becomes a nightmare. But the nice thing about this is that we can use this same kind of thermal analogy, this thermal network analogy that we constructed before for radiation networks, noting that we are now replacing temperature differences with radiosity differences and heat transfer rates with energy transfer rates. Now, this is great if we want to calculate radiosities, if we want to calculate, you know, temperature differences, energy transfer rates. But what about temperature differences? That's supposed to be the whole point of what we're doing here. Well, the issue is that once we figure out all of these quantities, now we have to go into a separate problem of trying to figure out what the temperature of an object is, or any other material property we want to find, say the emissivity or something like that. We now have to dig into figuring out what those things are as a function of their radiosities. And how can we do that? Well, remember the equations that we wrote down before. We had said that the emitted portion of the radiosity of a surface is simply its emissivity times the Stefan-Boltzmann constant times its temperature to the fourth power. So there's a connection there. But we also noticed that the radiosities were coupled as a result of the reflective behavior. And so what that meant was that in order for us to find, or at least calculate, the relationship of one radiosity to the other from the perspective of reflectivity, we had to basically know everything about the system before we actually started to solve the problem, or at least that's what it seemed like. And so the idea, or at least the general workflow for most of these problems, is to relate the radiosities to the net energy transfer rates between each surface, and then to use that information to try to create more information about the temperature and material properties of each individual surface. And that's kind of it. And like I had mentioned before, once you start adding enough surfaces, once you start increasing the resolution of these systems to the point where you can get detailed information about temperature variations over surface area, it's quite likely that the number of individual nodes, the number of view factors that are required to solve the problem, becomes so large that even like standard computers won't be able to do it. And so we would have to rely on very sophisticated software and sophisticated computers to solve radiation problems, which is why I've chosen not to talk about it in too much detail. But just because it's a hard problem doesn't mean it's unsolvable. And so nevertheless, many talented engineers, particularly those who work in space applications, use this problem-solving process of constructing radiation networks and finding view factors for specific geometries in order to try to make, the ISS work. And so far, it works. Fingers crossed. So clearly we're doing something right. And so even though this is just a brief glimpse, it's a brief glimpse into something that actually works. It's not just a theoretical abstraction.